The microcontroller on your Arduino and the microprocessor on your laptop are all run off of a central clock. And that clock is determining how fast a program executes on that piece of processing hardware. On the Arduino, your clock is running at something like 16 megahertz. That's for an Arduino Uno, which is what you're using in the lab. A microprocessor on your laptop might be running at 2.6 gigahertz, so quite a bit faster than what your Arduino is doing. So this clock, as I mentioned, is determining how fast a program executes. So each instruction might take, let's say, 1 to 3 clock cycles. Some can take more than that to actually execute. So something like a digital read might take 2 clock cycles, which would ultimately give me 2 divided by 16 million, or 125 nanoseconds to execute something like incrementing a variable or a digital read statement. That clock also supports a number of timers on your microcontroller. And these timers are what allow you to abstract some of that functionality using functions like the delay function that allows you to delay your code for a certain number of milliseconds, or the delay microseconds command as well. So some other examples of how I can use those timers. So there's my delay function that I'm familiar with. I also have some more advanced functions that also use time. So for the timers on my microcontroller, so the tone function, for example, can create a square wave on a particular pin. It's always at 50% duty cycle, so it's different than an analog write, but I can adjust the frequency of that square wave on that pin. Another example using one of the timers might be something like the pulse in command. And so pulse in will measure how long an input pulse takes on an input pin to the Arduino. So if I'm trying to, for example, measure the duty cycle of a pulse width modulated signal, this might be an interesting way to do it. And then finally, if I really want to get more complex and more interesting, as far as timers go, interrupts are a great way to do that. So they effectively let me create a multi-threaded Arduino program. So I can be doing something else while I'm waiting for a timer to complete. So one of the things that I'm interested in for a mechatronics system often is figuring out at what time certain things happen. And I might be interested in a kind of sensor value, trying to understand my sensor data from that point of view. So I have several functions that help me do that on the Arduino, so millis and micros. I'm going to focus on micros. So if I click on this, micros is going to tell me the number of microseconds since the Arduino board was last reset. It began running the current program. So this will go back to 0 only after about 70 minutes, and that's because this is returning an unsigned long, which is a 4-byte long number. So the other interesting thing to note is that this function has a resolution of 4 microseconds. So with the 16 megahertz clock, remember we said that a typical instruction might take something on the order of 125 nanoseconds. So we're not really going to be able to measure this. The smallest thing we should be able to see is 4 microseconds. So to look at this in a little greater detail, I've come up with the following sample code. So I have 2 global variables, time start and time end, that are going to give me my elapsed time to do something. I've designated those both, declared them both as unsigned longs. In my setup function, I'm just starting my serial port at 9600 baud. And now I'm just going to measure the time it takes me to do a couple math functions. So I have a is 3, b is 7, I have declared another integer, that C, and a float as D. And so I'm just going to print what these different things are, and this is the most important part. So I'm going to, before I do something that I want to measure the time that it takes for me to do that, I'm going to record that current clock value, or that current timer value. So time start will equal micros, and then after I do whatever it is I'm trying to measure, I'm going to say time end equals micros. So that will return the current version of that micros timer. And so in this case, now I'll just print out the time it takes, the elapsed time that a simple addition operation might require. And remember, the resolution on this is 4 microseconds. I do the same thing with floating point addition, with multiplication, floating point division, and then this is a more interesting one. The time it takes me to do a serial.println of enme 351 is awesome. And then finally, I'm going to measure the time it takes to do what I should expect to be a 1-second delay. So I can upload this, and there's nothing to look at on the Arduino, so I'm just going to open the serial port here. So it looks like everything requires 4 microseconds, but the serial print line requires 21.8 milliseconds. And the 1-second delay is pretty close to a 1-second delay. It's within a handful of microseconds of that 1-second delay. So it does a pretty good job of doing that. But you can play around with this, see how long different things take. One particular thing to play with might be changing the speed of your serial port. So for example, in my serial begin statement, I can now run my serial port at 57,600. And I'm going to upload that and open my serial monitor. And I need to make sure that that serial monitor is also set to 57,600 baud, which it is here. And so here I can see it only takes me about 3.5 or 3.6 milliseconds to send that same thing over the serial port. So it takes a lot less time than it did at 9600 baud, which makes sense. So for embedded systems, and in particular control systems, this timing can be crucial. I need to make sure something happens, for example, in an autonomous vehicle at a particular time. And for that we use something that's a lot fancier than an Arduino, but the same principle holds. I still have this central clock. I still have these timers that allow me to measure how long it takes and make sure that something happens when I want it to happen.